that it has 16 protons. Pretty much every element on the periodic table, the number indicates the number of protons. And if it's a neutral element, that means it has the same number of electrons as protons. So sulfur, a neutral element of sulfur, will also have 16 electrons. As you guys are probably thinking, atoms can become charged by gaining or losing electrons, and we'll go ahead and talk about that near the end of our session today. The molar mass is 32.07 grams per mole. And remember, the mole is going to be a counting number. This brings me, I always like kind of doing fun facts and thinking about ways that, chemistry is kind of interesting, which, it is. It's a cool subject. That's why I'm teaching it. This number here is, as we know, this number here, as we know, is called Avogadro's number, 6.02 times 10 to the 23rd particles. And I want you guys to think about this. How big is that number? If you stacked, let's say we had 1 mole of pennies, that would mean we would have 6.02 times 10 to the 23rd pennies. If we stack those up, it could go from here to the sun over 1 billion times. That stack of pennies would literally be going back and forth between here and the sun 1 billion times. That's a lot of things, and we need this number. It's an incredibly important number for us to realize, right, that these atoms are small. They, like, inside of me, I have maybe like 50 moles of atoms making me up, 50 to 100, probably closer to 100 for me because I'm a little bit bigger. But you guys get what I'm saying. And so the next thing that I want to discuss here is that this number down below actually means something else. It is not the mass number. So we'll jump back to this in a second. This number down below is also called the average atomic mass. And the average atomic mass is referring specifically to the mass of the atom, a single atom, and it's the averages of atoms. Because for sulfur, there are actually different types of sulfur atoms. So remember, sulfur has 16 protons, but we oftentimes will indicate elements in different ways. For example, we have sulfur 32, sulfur 33, and sulfur 34. These are the stable isotopes of sulfur, meaning that there are other unstable types, if you will. The number up in the upper left-hand corner, or the number after the hyphen here, is called the mass number. This mass number refers to the number of protons and neutrons, meaning that if I were to add, or rather subtract, the number of protons from this number up top here, I could get the number of neutrons. So 32 minus 16 would be 16. So sulfur 32 has 16 neutrons. 33 minus 16 would be 17. So sulfur 33 has 17 neutrons. And 34 minus 16 would be 18. So sulfur 34 has 18 neutrons. And notice that on planet Earth, there's a different abundance, or a different amount of these atoms. Most of sulfur on planet Earth is 94.99%. Coming in second is sulfur 34, et cetera. And so this number down below, 32.07, is the average mass of all those naturally occurring isotopes, so those 3 isotopes. When we're talking about this, this brings up our first, what I'll say, I like to say unofficial equations. So we have official equations and unofficial equations. Our unofficial equations are the ones not provided on the AP test. And it's not that they're like being jerks and not giving you those equations. It's just that these equations are kind of expected knowledge, if you will. And really, it's making sure you know how to take a weighted average. So all I did is wrote what a weighted average was into an equation form. So if there were 7 stable isotopes, you would literally just multiply the mass by the abundance 7 times for each one of the isotopes. For sulfur, since there are 3 of them, I'm going to take the mass, or the mass number, of sulfur 32, multiply by its percentage. Do the same thing for 33, multiply by its percentage. Do the same thing for 34 and multiply by its percentage. Now notice every single time I do this, I scooch the decimal over twice because I'm writing this in decimal, not percentage form. Decimal, not percentage form. So adding this up, literally all this data up, and what do you think you get? Hey, look at that. You get the average atomic mass, that number that is appearing on the periodic table. You can actually represent the mass spec data using one of these graphs, and this is actually our first really important graph to recognize. These are almost always going to be bar graphs where the abundance is represented on the y-axis and the isotope or mass number is represented on the x-axis. And if you ever see this bar graph here, they are only ever referring to the average atomic mass and nothing else. They'll often try to mess you up a little bit and say, oh, this is clearly photoelectron spectroscopy, or oh, this is clearly, telling you something else that it's not. This comes up a lot of times in multiple choice. I think in 2017 there was an FRQ that had this, but a lot of times these questions are related more to multiple choice. So in terms of atomic theory and individual atoms, I want to go ahead and pause really quick here and see, does anyone have any questions or things that you would like to ask just about what we've gone over so far? And I know there's going to be a little bit of a delay, so I'm going to kind of keep talking here while you guys are composing or thinking of your questions. And if I miss some of the questions, like I said before, the TA Dahlia is in chat doing an awesome job kind of helping us out here. Akshay, the fun fact about moles, so good. 1 mole of pennies would take up the volume of Earth. Isn't that crazy? Okay. The one I always tell my students that I totally brain farted on. If you tried to count to Avogadro's number, like literally said one number a second, 1, 2, 3, 4, 5, it would take longer to count to that number. It would take longer to count to that number than the universe has existed. Right? Isn't that amazing? I know. Cool. So a couple things. Okay, awesome. So some questions are rolling in here. So let's just go ahead and talk about this one last time. I want to make sure everyone understands what is kind of going on with these mass numbers here. I want to try this here. This was not working so great for me earlier, so I'm going to try it again now and see if it works. Cool. And then let's see. I think this is going to work here. So this right here is what we call the mass number. And it's the number of protons and neutrons. It's the number of protons and neutrons. Every single sulfur isotope has 16 protons. So the number of neutrons can be determined by subtracting that. I highly doubt they're ever going to ask you a question saying, how many protons is in this thing? What they'll probably end up asking you is some sort of question where they'll give you the mass spec data here, which is basically a mass spectrometer, goes ahead and looks at every naturally occurring isotope for an element and measures the abundance of that isotope versus the mass of that isotope. So for sulfur, there was only 3 existing isotopes, so we plot those 3 on the x-axis here. All right, so I am going to go ahead and move on. I think Dahlia is going to do a good job at kind of keeping an eye on things in chat. And like I said, I'd be more than happy to kind of keep checking on chat as we move along. So let's go ahead and move on here. We're actually going to look at molecular and empirical formula stuff. Molecular and empirical formula, I think, has a really cool application for ionic compounds, but the word molecular or molecule really is going to be hold steady for covalent compounds. So all the math that we're doing applies to ionic compounds, but it really should technically be more for molecular formula. You'll see what I mean when I kind of get into this. Molecular formula represents the actual molecule or compound with the correct number and type of elements, whereas the empirical formula represents molecules or compounds, in the lowest whole number ratio. So for ionic compounds are always in the lowest whole number ratio. They are always represented with very small amounts, the smallest ratio between the ions. For molecules, that's not always the case. For example, S2O2, disulfur dioxide, which is pictured down below here. Now, the empirical formula for disulfur dioxide is SO. There's one sulfur for every one oxygen. But SO, excuse me, would be its own thing. SO would be like a sulfur atom bonded to an oxygen atom. I don't know why it skipped there. Sorry about that. Maybe this isn't working as well as I was hoping. Sorry about that. So sulfur monoxide is the empirical formula, and it probably doesn't exist. So sulfur dioxide is the actual molecular formula for this thing. And this actually brings us up to our second unofficial equation. The molar mass of the molecular formula is equal to a whole number times the molar mass of the empirical formula. As far as this equation goes, when we're looking at the molar mass of the empirical formula and we're trying to determine what this chemical, what this substance, what this species is, then what we're essentially doing, let's go ahead and actually, boom, is relating that molar mass to the molar mass of the molecular formula with this whole number. So as far as relating empirical formula of SO to S2O2, that is going to be related by a small whole number of 2. Now, you probably are asking, and seriously, like when you guys think about this when you're in school, I always like to try to explain why to my students. Like, why are we interested in the molecular formula or the empirical formula? Specifically the empirical formula, because like I said earlier, this molecule SO probably doesn't exist. Well, the devices that we have to actually determine the amounts of elements and the ratio of elements in compounds, the best it can do is really only tell us the ratio. So we put this disulfur dioxide, right, S2O2 into a device, and it spits out saying, well, all I can tell you is that the ratio of sulfur to oxygen is 1:1. And what we need to go ahead and do is then do some other extra math here relating the molar mass of the empirical and the molar mass of the molecular formula to go ahead and find out what that actual molecular formula is. So next thing that kind of comes up from this is once you were comfortable relating the molecular and empirical formula, which we'll look at in a little bit of detail in here in a second, you also need to be able to actually determine the empirical formula. And every single one of you has probably done some sort of lab or simulation this year, because I know there's not a lot of lab opportunity with the pandemic currently going on. But as far as this goes, you should, I'm getting tongue-tied here, I'm gonna slow down. Determining the empirical formula is a lab that almost every single one of you has experienced. You can do this experimentally pretty easily. I usually do this with my students using hydrates with like Epsom salt or stuff like that. But really what you're trying to do is find the ratio of elements that are in the substance. So the first step for determining the empirical formula is to convert any possible percentages. So if you're given like percent compositions to grams, you're going to assume that 100-gram sample, you're looking at 100-gram sample. So if you know that your substance is 72% carbon, then 72 grams of that substance is carbon. So you're going to assume that you have a 100-gram sample. Once you do that, you're going to divide all the mole values by the smallest mole value to get whole numbers. And then our goal is to determine the elemental ratio of atoms within that molecule or compound. So what we're going to go ahead and do, is actually look at a question that kind of shows us how we can go about determining the empirical formula and then using that data to go ahead and determine the molecular formula. So that's what we're going to go ahead and do today. Find the molecular formula of a compound that is experimentally determined to be 66.7% sulfur and 33% oxygen by mass. The molar mass of the compound is 96.14. So we're going to actually go ahead and hold thing. Okay, cool. I'll go ahead and click through the process one more time, going a little bit slower here. So as you can see, when you do the dimensional analysis, we use the molar mass of sulfur to find out how many moles of sulfur there is. We use the molar mass of oxygen to find out how many moles of oxygen there are. And because it's the same amount of moles, this tells us that the empirical formula is in a 1-to-1 ratio, a 1-to-1 mole ratio. Once we determine the empirical formula, we are then going to use the 96, which is the molar mass of the molecular formula, and our unofficial equation. So once again, this is not an equation given to you on the AP cheat sheet. 96.14 is equal to N times 48.07. 48.07 is the molar mass of the empirical formula, and boom, N is equal to 2. That means there is a nice relationship between the empirical and molecular formula of a whole number of 2. So there we go. That's how we would go ahead and actually do this. So the empirical formula is SO, the molecular formula is S2O2. And I think now is a fantastic, great, cool time to jump in to quantum mechanics. Quantum mechanics is like literally one of my favorite subjects to teach. I always like to like drop the bomb though that my first time taking like college level quantum mechanics, I got destroyed by the class. I failed it. It's okay to fail classes, guys. It totally is. Because guess what? I took the class again and got a B. I know. You just had to, figure things out. Sometimes life is a little weird like that. So quantum mechanics is now one of my favorite things to talk about and discuss, especially on the qualitative side of things. So we're actually going to look at quantum mechanics from the qualitative side of things. And to start us off, I think a good place to look at is actually Coulomb's law. Coulomb's law basically states that opposite charges attract, like charges repel. And you will never need to use this formula here. You will never need to plug anything in. Sometimes your teachers will make you plug things in, and that's okay. Do what your teachers say, but on the actual AP test, this is not an equation you will need to actually use, but it is one that you need to describe. So I want to go ahead and show you kind of how you do this. The r squared refers to the distance between charges, and the closer those two charges are, the greater the force of attraction is, or repulsion. The magnitude of charge is represented by the letter Q, the variable Q. The more positive or negative that point charge is, the greater the force of attraction or repulsion. So what we're going to be doing during quantum mechanics is looking at how far the electron is from the nucleus. The electron is closer or further to the nucleus based on the shell or energy level that it's in. And the magnitude of charge is determined by the number of protons in the nucleus, the number of protons in the nucleus. So let's go ahead and jump into it and talk about some really key vocabulary words that I want to kind of make sure you understand as I get into this. So first off, what the heck are electron configurations? Well, electron configurations are just going to be a notation describing the position and location of an atom's electrons. When you first probably were learning this, you were going, what the heck is an S, a P, a D, and an F, 1s2, 2s2, 2p6, and now, hopefully at this point, you guys are like, oh, heck yeah, if I get an electron configuration question on the AP test, I'm going to jump up and down for joy, because literally all I have to do is look at the periodic table. One of the things that I think is really frustrating that students never seem to remember, and I always harp on my students about it, is the energy level. Energy level is a super important vocabulary word that you should remember. Energy level is this whole number, and it describes the distance of the electron from the nucleus. Electrons that are in higher energy levels are less attracted to the nucleus, and they do technically have higher energy and stuff like that. But really, at the end of the day, it is way better to describe the electron's energy level as how far it is from the nucleus. So if you're in an energy level of 7, you're further than from the nucleus than if you're in an energy level of 2. The sublevel describes the shape of the orbital. That's what the S, P, D, and F are. And then an orbital is going to be a region in space where the electron exists, 90% of the time. An orbital can have at most 2 electrons. So in order for those 2 electrons to be in the same orbital, they must have opposite spins. So that's kind of what we're looking at here is when we're doing electron configurations, we're describing where the electron is in terms of the energy level and the sublevel. You should memorize this chart. Once again, you should memorize this chart. Knowing the shapes of the orbitals is good. Once again, this is probably not going to be a question that they will outright ask you on the AP test. They may try to trip you up by saying, oh, it's really important that an electron is in a dumbbell-shaped orbital over a spherical orbital. Meh, that's probably not going to come up. The big thing is going to be the number of electrons in a single orbital and how many orbitals there are per energy level, because this helps us identify the electron configuration. Once again, you have access to these slides, so I would recommend you guys just checking out this chart and memorizing it. But at the end of the day, you probably won't get a single question that says like, oh, the d orbital is shaped like a 4-leaf clover. It's just a good visual for you. So I want everyone to take a few seconds here, pull up your periodic table. I want you to write the sulfur electron configuration out, or go ahead and just do it in your head. Make sure you have the ability to do this. I'm gonna give you guys a couple seconds while I kind of scroll through the chat and look at some of the things. I love the chat. You guys are doing so killer right now. Don't understand any of that. All right, hopefully you're thinking about your sulfur electron configuration. Hopefully you're thinking about your sulfur. You absolutely can use the noble gas shorthand. The noble gas shorthand is an excellent way to answer these questions and save you some time. But I'm just going to go ahead and do the full version here. It's 1s2, 2s2, 2p6, 3s2, 3p4. And here's the thing, ladies and gentlemen. Here's a basic periodic table. Here's a basic periodic table of the S, D, and P blocks. You'll notice I didn't include the F blocks here. Not that they won't ask you a question involving the F blocks. The F blocks are still super important, but majority of their electron configurations are going to be from this location here. So sulfur is located right here on the periodic table, And hopefully you remember or recall that as you do electron configurations, let's see if I can try this one more time. As you do electron configurations, you have to count left to right as you do so. So sulfur is right here. Hey, it's writing again. All right, cool. And there are 2 columns for the S. There are 10 columns for the D, 3, 4, 5, 6, 7, 8, 9, 10, and there are 6 for the P. 1, 2, 3, 4, 5, 6. Don't forget helium is right here, but it's not a part of the P block. That's why it's green like this. So sulfur being right here, the last row that I fill is the 4th column. That's where that 4 comes from. It's in the P block, and it's in the 1, 2, 3 row, 3rd row. Now, one of the questions that will come up about this is what this 3 means here. And the 3, remember, is referring to the energy level. The energy level. And the energy level tells us that the electrons are further or closer to the nucleus. So the 4 electrons that are in sulfur's 3p subshell are further from the nucleus than the 6 electrons that are in sulfur's 2p orbital, Once again, hopefully electron configurations are not going to be the most challenging thing that you will go ahead and see. But if it is, please feel free to ask us questions in Discord, and we'll point you to the right resources, really get you pro at doing electron configurations. So let's go ahead and move on here and continue looking at electron configurations in a little bit more detail. And what we're going to do is look at photoelectron spectroscopy. Photoelectron spectroscopy is a great way of showing or doing electron configurations in the laboratory setting. The laboratory setting shows us these really rad graphs where we plot the relative number of electrons on the y-axis. And on the x-axis, we plot the energy of the subshell or sublevel. This can be a little odd because if you notice, the x-axis seems to be going backwards. The higher the energy, the further to the left you are. We invert this graph here so that way it represents the electron configuration in the same order that you would read it. So for example, Sulfur has this 1s peak here, it has this 2s peak here, and then the 2p peak. Notice that the relative energy levels are close to each other, but different energy levels are far from each other. So the 2s and 2p are right here, and then we have 3s and 3p. Notice that the height of each of these peaks are only referring to the number of electrons. So once again, the height of the peak refers to the number of electrons. Questions that oftentimes come up for photoelectron spectroscopy type problems is where the relative peak is based on the x-axis. So how can we scooch this to the left or to the right? If we're scooching this peak here to the left, it means the electrons are more attracted to the atom because it takes more energy to remove those electrons. So photoelectron spectroscopy arises due to removing these electrons from the respective subshells or energy levels. And if we want to essentially look at and compare sulfur to, for example, chlorine, sulfur's 1s peak here is going to be further to the right than chlorine's will. Chlorine will probably be something like here. The reason that chlorine's peak will be here is because chlorine has more protons, and based on Coulomb's law, the greater the number of protons, the more attracted electrons will be to the atom. So those are basically the types of questions and things that you will get for photoelectron spectroscopy. Another really great question that could come up and like pumps me up, gets me super excited, is they'll give you a photoelectron spectroscopy graph. And these are pretty obvious. Like you look at them, you're like, okay, these are referring to electron configurations. And sometimes they'll just straight up ask you, what's the electron configuration or what's the identity of this element? And if they ask you that, you're like, sweet. That's an easy question. I can answer that. Woo! We are cruising. We are doing so good. I am like super proud of everyone for keeping with me and asking excellent questions in chat. Thank you, thank you, thank you, thank you, thank you. What we are going to pretty much be ending with here is the periodic trends. And also just talking about some things that are important in the world of forming bonds, specifically the Octet Rule and stuff like that. Once again, if you have any questions, hopefully you're throwing them into chat, and Dahlia and I can spend some time afterwards looking at chat and kind of asking some good questions or answering some good questions. But thanks, Dahlia, so much for answering these live time. So with this being said, the Octet Rule. Hey. Hopefully everyone here has heard of the Octet Rule, and even if you haven't heard of the Octet Rule, you see this prefix oct and are thinking 8, right? Oct means 8. The Octet Rule, hopefully as a reminder, refers to the number of valence electrons that an element has. Valence electrons are the electrons that are in the highest energy level, and determining the valence electrons is actually pretty much just the ability to count these. I'll show you what this looks like on the next slide. When atoms form chemical bonds, they tend to gain or lose electrons such that they have 8. We'll also look at molecules or covalent compounds, and a large goal of theirs is to go ahead and have a total combined number of 8 valence electrons. But as I'm sure some of you remember from Unit 2, atoms don't have to have 8 valence electrons. So I like to sometimes call this the octet tendency or the octet guideline, not really the octet rule. Ions are going to be charged particles that become charged by gaining or losing electrons in order to get that 8. And when atoms gain electrons, they're going to be negatively charged. It seems counterintuitive, but if you take a moment to pause and think about this, gaining electrons, gaining negatively charged things makes you negative. So when we're looking at this, negatively charged ions are called anions, and they become negatively charged by gaining electrons. Positively charged ions are due to the fact that they lose electrons. So metals tend to be cations, non-metals tend to be anions. So let's go ahead and look at this. This hopefully is ingrained in every single one of my AP chemistry students and your guys' brains at this point. Counting valence electrons is as easy as counting from the left to the right, and we always skip the transition metals, the D block here, because when we go here, it drops down in energy level. The D block always adds electrons to a lower energy level after the 4s of the 5s here. So for example, if we're looking at sulfur, because that's been our main go-to element for the day, sulfur has 1, 2, 3, 4, 5, 6, because once again it's right here. Being able to count number of valence electrons is going to be really important, not just for determining the ionic charge, but also doing Lewis structures. Ionic charge is incredibly important. Being able to determine the charge of ions based on the placement of the periodic table is like high priority. Now, what you'll see is I've labeled each one of these columns with a charge. These columns here are represented as +1, +2, +3, -3, -2, and -1, respectively. These columns each have their respective charge due to what they want to try to gain or lose in order to have an octet. Let's use sulfur as an example again. Sulfur is right here. In order for sulfur to get 8 valence electrons, remember sulfur had 6, it needs to gain 2. And you'll notice that when something gains 2 electrons, it has a -2 charge. So essentially everything in this column has 6 valence electrons, and everything in this column, when it forms an ion, will have a -2 charge. And also notice the language I'm using, when it forms an ion. It's not that these elements in this column are always charged. They're only going to be charged when they're in ionic compounds, so don't fall into that trap there. Now, a couple other weird things that I want to point out. If you look here, zinc is this element. Zinc always has a +2 charge. Silver is right here. Silver always has a 1+ charge. You need to memorize these. These are the two most common elements that don't have a valence electron count, if you will, and you need to know their charges. And I want to point out that here in this column, this is the column of 4 valence electrons. You can't really gain or lose 4 electrons, right? That's not really a thing that we can go ahead and do. So as far as this goes, elements, I believe this is tin and lead. I know this is lead, but tin here will generally lose either 2 or 4 electrons in order to form an ion. This is just how they react. You need to memorize that they can have these charges, but you don't need to explain why. So as far as this goes, the D block elements, so pretty much everything else in the transition metals, can lose different numbers of electrons and form different ions. For example, copper can either have a +1 or +2 charge. Iron can either have a +2 or +3 charge. Manganese can have like 5 different charges. Manganese is weird. It has a lot of different charges and stuff like that. So just be able to look up the periodic table and know the charges for all of these. As far as the common polyatomic ions, you need to know a good amount of them. Luckily, polyatomic ions, you can determine what their charge is based on what they're bonded to, And if I'm looking at the 2 and 4 here, I can figure out what their charge is based on also what they're bonded to. So for example, let me see if I can try to write this out again. Like I said, the usage of Vimeo is new to me today. Cool. If I look at, for example, PbCl2, I know that lead in this example has a 2+ charge in order to form a bond with chlorine in this ratio. See, gosh darn it, I don't know why it switched. It ruined my cool joke. I'll come back to this in a second here. Go ahead and close that. Now it's all funky. There we go. So PbCl2, for example, I know it's 2+. All right. Dang it, ruined the punchline, ruined the best part. My whole spiel here. This is one of my favorite jokes of all time. The 2019 Nobel Prize in Chemistry went to this team. I don't know why no one thought to look up here. All right. How's everyone doing? Let's take a, I think it is. Let's take a temperature check. How's everyone feeling out there in the world of chemistry 5-able land? Give me one word describing how you feel about Unit 1 chemistry, the atom and elemental properties. Exhausted. I feel you, man. Yeah, I'm tired too. Good. I love Unit 1. I love Unit 1. I think Unit 1 is really kind of cool. All right, yeah. Okay, so the periodic table, right, is right here, the periodic table, and obviously this part is missing. So the joke is just saying like, oh my god, there's a whole bunch of elements up here, and that's the joke. Solid, nice, Amir. All right, pretty good, phenomenal, cool. All right, so let's go ahead and move on. We're gonna finish up here pretty soon. I'm really stoked. We're doing great on time, and we're gonna look at the periodic trends. I'm almost finished, Jay, with Unit 1. So I know, right? Pretty much all of Unit 1 we did in Honors Chem. I totally agree with that. So the periodic trends are going to be pretty much the last thing that we look at today. And there's going to be two really important things that I want to point out when we get into this. But first, let's make sure we know what all the periodic trends are. The atomic radius is referring to half the distance between the nuclei of two identical atoms bonded together. To be perfectly honest, this is just referring to the atomic size, the size of the atom. Electron affinity refers to the amount of energy released when an atom gains an electron. This one comes up so often, but it's not really that common of a periodic trend. The big one, though, the big vocab word is ionization energy. Ionization energy is referring to the amount of energy required to remove an electron from an atom. And last but not least, the electronegativity refers to the atom's ability to attract electrons in a chemical bond. You should just know each of these vocab words by heart. Like every time I ask my students these, I love it when they can just state exactly what these vocab words are. As far as the atomic radius goes, the trend is that it increases to the left and down. So the biggest element on the periodic table, our current periodic table, would be francium, and the smallest element in terms of radius is helium. As far as the other trends, ionization energy, electron affinity, and electronegativity go, they increase up and to the right. Sorry about that. Whoa. They increase up and to the right. So you need to just be comfortable with each one of those because, yeah, they might just straight up ask you a question that says, hey, calcium has this radius. What's the calcium of potassium? Hey, carbon has this ionization energy. What's the ionization for energy for silicon? And being able to recognize the elements based on where they're placed on the periodic table to the relative trend is super duper important. But with that being said, the two key things that I wanted to talk about with you guys today in terms of periodic trends is this. When they ask you why a periodic trend occurs, you cannot just say, oh, because the atom is further up and to the left. That is not a legitimate reason or a good justification. When we're trying to justify why a trend exists, you want to either use the energy level of the valence electron or the number of protons in the nucleus. So let's look at the energy level of the valence electrons. Remember, energy level determines how far the electron is from the nucleus. And the valence electrons are going to be the ones furthest away from the nucleus. Oftentimes, the valence electron's location will explain the trend, especially if we are comparing two elements in the same column. So let's go back to our friend sulfur. Sulfur has a larger atomic radius than oxygen, and we know this just due to the fact that it's further down on the periodic table compared to oxygen. However, why is sulfur bigger? Why does it have a larger radius than oxygen? Well, because its valence electrons occupy a higher energy level. If energy level is describing the distance of the electron from the nucleus, then if your valence electron is further from the nucleus compared to oxygen's, right, then you're just going to have a larger atom. We also know that sulfur has a larger ionization energy than selenium. So notice I'm comparing atoms and elements that are in the same column. Hopefully you guys are all looking at your periodic table here. Sulfur has a larger ionization energy compared to selenium because its valence electrons occupy a smaller energy level and are therefore more attracted to the nucleus. If the valence electrons are in a smaller energy level, then they are closer to the nucleus, meaning that those positively charged protons want to hold on to those electrons as best as they can. As far as nuclear charge goes, nuclear charge refers to the number of protons in the nucleus. The more protons you have in the nucleus, the more positive you are. The atom is, rather. Not, I mean, you could be positive too, right? Yeah, I'm positive. So as far as this goes, nuclear charges will tend to explain the trends of elements that are in the same period or row, left and right. So sulfur, when we're comparing to argon, has a larger atomic radius because argon has more protons in the nucleus, and it's able to attract the valence electrons that are in the same shell, right? The same energy level.